Continuing the applications of exponentials and logs, let's knock over a couple more questions. So it's known that these 2 points lie on a curve of the function f of x equals a times b to the x, determine values of a and b. So the usual approach to these problems will be to sub some values in. So we've got 12 as y, or f of x, equals a times b to the 1. So that's 12 equals ab. Then let's do the other one. So 3, 2, 4 equals a times b to the 4. That's 3, 2, 4 equals ab to the 4. All right, what do you want to do? Well, what I'm anticipating here is let's solve this for b. So what I'm going to do is, yes, let's just try solving it for b and see what happens. I'm going to go b equals 12 on a, and then I'm going to sub b equals 12 on a into this. And again, let's just see what happens. 3, 2, 4 equals a times 12 on a to the 4. Okay, now we've got 3, 2, 4 equals a times 12 to the 4 over a to the 4. Now, what's going to happen is that will cancel with that, leaving us with a to the 3. What I'm going to do is throw a to the 3 over there and say that I've got 12 to the 4 over 3 to 4. All right, now, what is 12 to the 4? Okay, that's the hard part. Second part then is the fraction will simplify down, and then we're going to have to third root both sides. Okay, so this really is, at this point, a calculator problem. This is, mind you, if you're thinking this wouldn't be the way I would do it, correct, but let's just go with this and see what happens. So I've got 12 to the 4, which is that number, over 324, which is that number. Okay, again, without a calculator, that's very difficult to do. So we've got a to the 3 equals 64. The third root of 64 is, in fact, 4. So a equals 4, and when I sub a equals 4 into that, I get b equals 3. Okay, now, is there another way for these problems, or to do these problems? And the answer is yes. Okay, so I'll show you the other method to do them, and let's just see whether this is a little more efficient. Okay, so let's do the substitutions again, and I've got 12 equals a times b, and I've got 324 equals, what was it? A times b to the 4. Okay, now this is equation 1 and this is equation 2, and what we've been doing basically is substitution there in that first instance. Now, why not elimination? Okay, well, a lot of you will think that elimination can't happen on this because 1 take away 2 doesn't work, or 2 take away 1 doesn't eliminate, but who said you had to subtract or add? Okay, so here's what I'm going to do. I'm going to do 1 divided by 2. Okay, I'm going to create a third function, which is the result of dividing the first function by the second function. All right, so what happens is the a's cancel out because a divided by a is 1. I've got b to the 3, and all I need to do now is work out how many times 12 goes into 324. Okay, so I'm going to put 12 into 324. That goes twice, and remainder 24, 6, 8. Now, 12 goes into 84, 7 12s, 27. Okay, now I need to third root both sides, which means that b equals 3. Right, now I use the b equals 3 and jam it into one of these. I'm going to do 12 equals 3a, a equals 4. Okay, so note that this method here will get us the same solution set as the substitution, but the substitution method is a hell of a lot harder. Okay, so wise decision making is probably the order of the day here. All right, so find an exponential model of the form y equals a times b to the x to fit the following data, state correct, values correct at 2 decimal places. All right, I'm going to do this 2 ways. I'm going to pretend that we're not told the form and it just says find an exponential model. So I'm going to do this by hand. So the way we've been finding exponential models is using that basic approach of a equals A0 multiplied by b to the kt. Okay. In this instance here, we've got y equals the initial value. Okay, so whatever our initial value is, times any base we like, kx. All right, so what is our initial going to be? Well, that's when y is equal to, or x is equal to 0. The y value needs to be that. And when I raise any base over here, 0, b to the 0 is going to be 1. That needs to be 1.5. So our initial value, this value here, must be 1.5. So I'm going to rewrite that as y equals 1.5 times. Now this is the time I can choose any base I want. And because I feel like it, I'm going to choose base 2. So the kx. Okay, now what I'm going to do is substitute that coordinate point in there for x and y and get my k value. And once I've got my k value, then I've got my equation or my relationship in terms of y and x's. Not in terms of y and x's, y equals in terms of x. All right. Now, this is saying that when x is equal to 2, y is equal to a half. So let's put a half in there. 1.5 times 2 to the k times 2, which is 2k. Okay, so now we're going to do a half divided by 1.5, which is 3 on 2, equals 2 to the 2k. That is going to chop that out and be 1/3 equals 2 to the 2k. Okay, now let's switch to log form. Log 2 1/3 equals 2k. K is equal to half log 2 1/3. Therefore, my equation is y equals 1.5 times 2 to the half log 2 1/3 x. All right, let's just try it out to see whether that is going to work for us. Okay, so we're going to type in 1.5 multiplied by. Now our base is 2. Hit the power, whoops, not the line button, hit the power button, and we're going to go half multiplied by log, which is shift 6 for the log template, 2, 1 on 3. And our x, let's just try it out for this value of x here. X is equal to 0. So times 0. Good, that's a good sign. Put in 2, let's see what happens. Should be 0.5. It is. Put in 4. Should be 0.17. Pretty close. 5, etc., etc. So we have hit the model. All right, so there is one possible model. Now there's another way to get models. Okay, so another method that the book explains, and it's my less preferred method, is to go to statistics and to type your x values into list 1, 5 and what is it, 10, and 1.5, 0.5, 0.17, 0.09, 0.006. Okay, now don't worry when you see that, that's just 6 by 10 to the negative 3, which is in fact 0.006. All right, now at this point here, what we're going to do is go to calc and use this thing called regression. Now what regression does is fits a line of best fit to the points that you have included there, okay? And what kind of model do we want? Well, we've got, we can pick from the menu here, okay? So we can pick linear regression. That means fit a straight line to these points here. Well, we don't want a straight line. We don't want a quadratic. Okay, this is not supposed to be modeled by a quadratic. It's actually a linear function as described by this here. So what we're going to do is ask it to do exponential regression. And it goes, all right, where's your x values? Where's your y values? All right, so that's correct there. I've put the x's in list 1 and the y's in list 2. Let's hit OK. And note that it tells us that a possible equation is y equals, so the a value is here, that's 1.5, multiplied by e to the, so they've chosen base e as the calculator always does. Our b value there is negative 0.5 5, 3. Let's go up to 3 decimal places because the question doesn't really say anything about it. All state values correct to 2 decimal places. Okay, so yes, it does. So we'll get rid of that. 0.55x. Okay, and basically that will yield the same results as our equation over here. We did this one by hand. This one, the calculator did the hard work for us. Okay, and you can see here what the calc does is it plots the points and then fits a line to those points. Okay, so there's our two possible equations. Try it out and see. So slam in values of x into their equation and you'll note that it produces the same values as ours does. All right, so there's the homework 13H. I want you to finish off. I think I set from 1 to 4, so that's now 5 to 8 plus those and those. You have the chapter review, but before we get on to that, we're just going to go through one more modeling exponentials example. This is the one I'll give out in class today. All right, so we've got a population of amoeba has unlimited food and grows according to the rule blah, blah, blah. P is the number of amoeba T days after the experiment began. Initially, there were 500. 3 days later, there were 700. All right, this n value, remember, fits the basic model of A equals A0 times B to the KT, where this A0 or this n is our initial. So this tells us that initially there were 500 amoeba. Actually, state n is equal to that. Don't need the context. All right, find K. So we want the K value. So let's just pop that in. P equals A0, which is 500, multiplied by, they want us to use base E, so we've really got no choice here. B has to be base E to the KT. So we're going to use that as our basis. All right, now, what are we going to do? 3 days later, there were 500. There was 700, rather. So we're going to go 700 equals 500 times e to the, and 3 is days, t is in days. Okay, so it's going to be 3k. Bang, bang, 7 on 5 equals e to the 3k. K is equal to, or 3k is equal to log e 7 on 5. K is equal to 1/3 log e 7 on 5. Okay, so that means that our rule will be, let's complete our rule. A, or no, not that one, let's use the variables. P equals 500 multiplied by e to the, K value 1/3 log e 7 on 5 t. All right, find the population after 7 days. Okay, so here's where we revert to the calculator and ask the calculator a question. Okay, so I'm going to go 500 multiplied by, now you find E at shift 4, 1/3 multiplied by, you find log E, shift 5. You want the natural logarithms, that's shift 5, 7 on 5, multiplied by T, which is 7 days, which is 7. Okay, so find the population after 7 days. So at the conclusion or after 7 days, what does T equal? T is the number of days after. So after 7 days. Okay, so what we're going to say is that, so let's write it out. P equals 500 multiplied by e to the 1/3 log e 7 on 5 multiplied by 7. P equals 1096.315 ... Therefore, 1096. How do you spell amoeba? I don't even know how to spell it. A-M-O-E-B-A. A-M-O-E-B-A. Okay, so why didn't I write the exact value there? Well, after 7 days, this is how many amoeba are expected to be there. So basically, there's that many complete amoebas, and they're growing another one. Interestingly, if this actually was the value 6 or 7, the answer would still be 1096 amoeba, because we still haven't completed that 1097th amoeba at this stage. All right, when will the population pass 2,000? So that's a standard solve problem. We're going to go 2,000 equals 500 multiplied by e to the 1/3 log e 7 on 5 multiplied by t. This is basically saying what value for t will give us a population of more than 2,000. So I'm going to go solve on the calculator here. Solve. Let's grab this thing here. Let's go 2,000 equals it. Let's get rid of the 7 and replace it with an x, comma x. All right, so it's t equals 12.3602 dot 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 dot. All right, so when does that happen? Okay, so that happens after 12 days, or probably more specifically during the 13th day. Okay, so after 12 days, we still haven't got enough. So actually, that's wrong. We shouldn't write that. It is not 2 answers, because after 12 days is like, what, 14 days? 700 days? Okay, so when will it pass 2,000? It's going to pass 2,000 during the 13th day. Okay, during the 13th day. Okay, let's just modify this question a little bit and say, after how many days will the population be more than 2,000? Okay, so if you get your answer of 12 here, okay, what we're going to do though is the answer to this question here, after how many days will the population be more than 2,000? It's actually going to be 13 as our answer. So 13 days need to pass before the population is more than 2,000. And this is looking for the number of days. So this specifically is 13 here, okay? Whereas this answer here is during the 13th day. So again, quite interesting ways to interpret these problems. Okay.